we have talked about one method of converting analog information into digital form, and that is delta modulation. It's a very simple technique by which one can represent analog messages in the form of a sequence of positive and negative pulses, which is what is eventually transmitted onto a channel, and let's say you can carry out digital communication this way. Another method of doing this, which is also in fact which is perhaps somewhat more popular, is the pulse code modulation, with which you are partly familiar in the context of analog to digital conversion in other courses, and that's what we will discuss today in the context of digital communication. Like delta modulation, this is also a digital pulse modulation scheme, but the approach is quite different, as I will show in this block diagram. You start with sampling the signal at a suitable rate. So there is a sampler, a message signal MT is passed through this sampler. Of course, when you do sampling of any signal, it is assumed that you do it at a sufficient rate so that you don't lose information, and you know what that rate is, the Nyquist rate. That is, if the signal MT has a bandwidth W, then you must use a sampling rate at least equal to 2W samples per second. In fact, also it is desirable that if you are sampling at 2W samples per second, you make sure that MT does not have any component above W. Other way around also holds. If you don't do that, you are going to have some kind of distortion with which you are familiar, aliasing distortion. Right? Take for example the case of your voice signal. Voice signal does contain components even beyond 4 kHz, but for most purposes the quality of voice signal hardly suffers if you were to band limit it to within 3.3 kHz or so, right? Therefore, we can say that we can sample at twice the maximum component, which is roughly taken to be 4 kHz, and therefore you sample at 8 kHz. But then you must make sure that the voice signal before being sampled is low pass filtered by a filter whose bandwidth is about 4 kHz or less, right? About between 3.3 and 4 kHz. So because it may contain components of higher frequencies which may not be of interest to us, but which if allowed to be present will cause aliasing distortion, which we don't want.
Which distortion?
Aliasing distortion. Maybe I should just remind you, these are the spellings. Aliasing. After sampling the signal, the most important step that you carry out in a pulse code modulation system is that of quantization. There is a quantizer. We will soon see what a quantizer does, and immediately following that there is an encoder. These three basic building blocks are the key components of a pulse code modulation system. Excuse me. The main function of the quantizer is to take each sample and represent it in one of a prefixed number of levels. Excuse me. That is, unlike the sample value which can take any value over an infinite range, the quantizer converts this into or transforms this continuous valued variable into a discrete valued variable. I think it is best illustrated by means of a picture which I have here. It's the same picture that you have that we talked about, the sampler, the quantizer and the encoder. Let's say that this is your continuous time, continuous valued signal, right? So it's continuous both in time as well as in amplitude. The first thing that you do is sample it. So you're talking about sampling at the Nyquist rate, and let's say these are the samples that you have obtained after sampling, right? These are the values that you have. Now these values lie on a continuous axis, amplitude axis. What you now do is assign each of these sample values to one of these discrete levels which I have indicated by horizontal lines. And the manner of the assignment is you assign each sample value to the level, to the value which lies closest to it. Okay? So for example, this sample will be given the level number 4, assigned to the level number 4, this one to 6, this one to 8, this one to 9, next one also to 9 because it is close to 9. Next one to 7, next one to 6, and so on. And therefore, now we will be transmitting not the actual sample values, but the levels to which these sample values are close. And these levels are discrete in nature. Further, these levels which are level outputs which are coming out of the quantizer are not transmitted as such. One could do that. If you do that, then instead of PCM what you get is quantized PAM. If you were to transmit the quantizer output directly, you could do that. It would be, see, the sampler output is normal analog pulse amplitude modulation scheme. After the quantizer, it becomes some kind of a quantized pulse amplitude modulation scheme. And even that could be regarded as some kind of a digital pulse modulation scheme because of the process of quantization. But usually it is preferred that instead of transmitting it in the quantized PAM form, we carry out some encoding of each of these levels and transmit it finally in a binary form. So the job of the encoder is simply to give or introduce a binary representation to each of these levels, and typically that binary representation will use a certain number of bits in a word, and those bits of the word are transmitted in the form of a sequence of binary pulses. So what the PCM output that I have got here is really a binary pulse representation of each of these numbers. I have shown this here. I have taken a few of these samples, the first few samples 4, 6, 8, 9, and represented each of them by a 4-bit word, assuming that my total number of levels is only 16. The number of bits that I will require for representation will depend on how many levels of quantization I have, right? Assume that we have only 16 levels of quantization, then each sample would require 4 bits for representation, and we may have a sequence of binary digits like this which we eventually have to transmit. This is a representation for 4, for 6, for 8, for 9, and finally what you may transmit is a pulse sequence like that. So these are the binary coded pulses that form the output of the PCM system and which are finally transmitted onto the channel. Yes, please.
Sir, the two collective ones, why are they not contained inside I?
should be considered?
It depends on how you represent your each one. How do you represent a 1 or a 0? There are many ways of doing it. I could represent a 1 by like this and a 0 like this, right? In which case what you are saying is right. I could also represent a 1 by a pulse like that, half the duration, right, and a 0 like that, right. So anyway, we will discuss these various possible representations of digits onto pulses, and that's what we will discuss when we talk about line coding. There are various representations possible, and depending on which representation you use will decide the actual nature of your pulse strain that you finally have to transmit. Any other question? Okay. Now, so this is a very conceptually a very simple process. The process of converting analog signal into a binary representation by the PCM process. It's a very simple, conceptually simple process. Though implementation wise it's much more complex than, let's say, a delta modulator, because you have to really build an analog to digital converter. The implementation of the quantizer is a non-trivial operation, and I'm sure you're all familiar with that fact. However, at the moment we are interested in looking at not the implementation of the A to D converter, with which we are already quite familiar, but about the communication aspects of PCM. And the first thing that we'd like to look at is the bandwidth requirement of a PCM system. If you have to start with, you have an analog signal. Let me talk about bandwidth requirement. As I said, to start with, I have an analog signal, let us say of bandwidth W. The question is, do I continue to use a bandwidth which is of the order of W, or do I eventually end up using a bandwidth which is much larger? So that is a question we like to address and work out quantitatively how much it is. To do that, let us introduce a few parameters of the quantizer. Let's assume that the quantizer of the associated with the PCM system of interest has Q number of quantization levels. And for convenience, let's assume that Q is chosen to be a power of 2. It will be convenient to do so because we have to eventually give a binary representation to each level, right? So it will be efficient if you do that by choosing Q to be a power of 2, that is 2 to the power n, where n is an appropriately chosen integer. Which implies that n will be the number of bits in a word that you will be requiring to represent each level, right? The encoder will have to use a word length of n bits. That's the implication. And n is obviously equal to log q to the base 2. And these many pulses are needed to represent each sample. Let's say that your signal has a bandwidth W. Your message empty has a bandwidth W. So this is the bandwidth of empty. Then what will be the minimum sampling rate that you'll have to use? So sampling rate is 2W. Now, what determines the bandwidth of a pulse strain?
The rise time.
Or roughly we'll say, well, ideally we all appreciate that if we're talking about an ideal pulse strain, the bandwidth is going to be infinite, right? So we are talking about some more practical measure of bandwidth here than the theoretical Fourier transform extend the span of the Fourier transform of the signal. That will be of course infinite. We are perhaps talking about the bandwidth in which most of the signal energy lies, right? And suppose you have a pulse of a certain kind, let's say an ideal pulse of width tau. Roughly what can you say about the bandwidth of this? Any idea? I'm sure you can say something.
It's a sinc function.
The Fourier transform of this is a sinc function, right? One rule of the thumb is that most of the energy lies in the main lobe of the sinc function, right? Whose width happens to be the reciprocal of the pulse width, right? Makes reasonable sense? So we'll say roughly we can say that if we are using a pulse train with each pulse having a width of approximately tau seconds, then the bandwidth associated with that pulse train will be of the order of 1 by tau hertz. That is, most of the energy of the pulse train will lie in this bandwidth. It's essentially a convenient measure of bandwidth rather than a precise measure of bandwidth. Alright, if your sampling rate is 2W and I'm going to represent each sample by how many pulses? N pulses. So number of pulses or pulse rate at which you have to transmit pulses is going to be 2NW. If I'm using a pulse train of this rate, what is the maximum pulse width I can have? Obviously of the same duration. Maximum pulse width I can have is 2NW, 1 by 2NW. So maximum pulse duration tau is of the order of 2NW, 1 by 2NW. Sorry. Is that okay? And therefore, what is the bandwidth of the this will be the minimum bandwidth, because we are talking of the maximum pulse width that we can have. So this is some kind of a lower bound on bandwidth that we are talking about. Is of the order of 2NW. In general, if you want to be more precise, it will be some constant times this 2NW, where k is a appropriate constant of bandwidth depending on what definition of bandwidth we precisely use, whether we decide on the main loop bandwidth or some other measure of bandwidth. So it may vary between factor like 0.35 to 1.2 or something like that, depending on the precise definition that we use to say, to decide the, what is the definition of bandwidth you are going to use. Yes, please. Question.
This 2NW is just the rate of sample, the rate of pulses that are to be sent.
Right.
But the bandwidth required for one individual pulse might itself be larger than this 2NW. So the bandwidth requirements can be more. Therefore I have said this is a lower bound, right? If your pulse width happens to be less than 1 by 2NW, which you can use if you wish, you will end up using more bandwidth. But you can't use a bandwidth less than this, right? So this is some kind of a lower bound on bandwidth that a PCM system must be associated with. You have precisely got it right. It is a lower bound. Or in other words, I can say that it is 2kW log q to the base 2. So therefore, you are increasing the bandwidth from W to this factor, which is an order of magnitude increase and depends on how many quantization levels you have, right? The larger the quantizations, number of quantization levels you have, the finer the quantization you carry out. Of course, that will lead to a more accurate representation of your signal, right? But it will also introduce a larger bandwidth sacrifice. It will also require a larger bandwidth for transmitting the signal. So
What is K?
K is a suitable constant which will depend on the precise nature of definition that you use to use for understanding what bandwidth is, right? Like for example, the argument that I gave that a pulse may be considered to have a bandwidth equal to the width of the main lobe of the sinc function associated with it in the frequency domain is one possible definition. You could use some other definition, right? For example, you could decide to use 99% energy bandwidth, right? That is the bandwidth in which that portion of the bandwidth where 99% of the total signal energy lies or lies. So in which case your value of k may turn out to be different. But nevertheless, the order of magnitude will not change, right? This is one aspect of PCM when we talk about using it for communication, digital communication. Now the other aspect is that the process of quantization introduces errors, introduces noise right at the transmitter itself. Now this is unlike other communication processes. You don't introduce noise at the transmitter deliberately, right? Here, since you are not sending the precise value of the sample but only an approximation of it in terms of the quantization, you are actually introducing or incorporating certain error of representation directly at the transmitter itself in the process of encoding, which may sound to be an undesirable thing to do, right? But the advantage is, in spite of this error that we introduce, this is a controlled amount of error which we can control by looking at our requirement and deciding on how many quantization levels I must use. The advantage that I get is that of digital communication, that is, I am able to eliminate noise that is introduced later in the channel, right? Very, very significantly. But nevertheless, we must be aware of this fact that the process of quantization is a noisy one, and we must also be able to figure out how much noise is being introduced, how much error is being introduced. So the next thing that is of interest to us therefore is to be able to calculate how much quantization error or quantization noise, as we call it, is being introduced. Let's try to calculate that. In doing this, I will be using this simple set of definitions. These solid lines are denoting here the boundaries of various quantization levels. Boundaries of various quantization levels. So x0 is the lower boundary here, and x3 is the upper boundary. Well, I have only got 4 levels here, or let's say 4 regions here, but you could have more, right? And m sub i's, m1, m2, m3, they represent the middle point as shown by the dotted lines of the ith interval. So m sub I is the midpoint of the ith interval. Let's assume that your signal sample values, which I am going to denote by x, has an excursion between a lower limit of a and an upper limit of b, right? Each sample coming out of the sampler, which I am going to represent by x, can take a maximum value of b and a minimum value of a. Alright? So b is the maximum value of x, and therefore that will be represented by x3 or whatever is the largest, highest level you have, and a is the it should be minimum here, minimum value of x. And let's say there are q number of quantization intervals, and therefore each interval, each quantization interval is obviously equal to b minus a upon q. So we are going to use this framework for our calculation of quantization error. If the signal value happens to be here, the level that will be assigned to it will be the middle point, right? And therefore this much error will be introduced in the process of representation. If it happens to be here, this much error will be introduced, right? So we can see that the error that is going to be introduced is going to be random in nature, depending on what the value of x turns out to be, and it's going to be both positive, equally likely to be positive or negative, right?
So we will model this error to be some kind of a random variable and then calculate what its mean square value, okay, and that will give us some idea of the quantization noise that is being introduced. That is the procedure we are going to follow. Any questions? So let us start this computation. So let us say that the sample value is x, okay, and then this is quantized and the quantized value is represented by x sub q, quantized value of x this is obviously going to be equal to m sub I, which is the midpoint of the interval in which x lies. Or I could say that it is equal to m sub I if x lies in the interval x sub I minus 1 and x sub I, right, because the middle point of the interval whose boundaries are x I minus 1 on the lower side and x sub I on the higher side is precisely equal to m sub I, and that will be the quantized value of x, which I am going to represent by x cube. What is the quantization error? Is going to be x minus x cube or x minus m sub I. Is it okay? Any questions? Nothing very complicated, it's all very straightforward. Alright, what is the quantization noise power or mean square value of this error? So quantization noise power I am going to define it as the expected value of x minus x sub q square, right? You are familiar with these kind of operations, which will be take x minus x sub are now denote, capital X is being used to denote the random variables. The actual values that they will take will be denoted by small letters. So small x minus x sub q whole square fxx dx integral of this, where what is fxx? It's the probability density function of the random variable x, and x is the sample value at the sampling instant. Now we have to evaluate this integral.
The limits are from A to B.
I have deliberately left the limits to be open at the moment. I am now going to rewrite this integral as the sum of q integrals, because the total integration range of course is going to be from A to B, which I can divide into various sub integrals, the ith of which goes from x sub I minus 1 to x sub I, x minus m sub I whole square fxx dx. Fine. Actually we will be interested in computing the signal to noise ratio that comes out of the PCM quantizer. So let's also do a similar exercise for the signal itself. That is, let's look at the signal power available to you at the quantizer output.
that will be obviously equal to expected value of xq square, because the signal sample that is coming out is xq, which again I can write in this form: xq is equal to m sub I, so m sub I square, and that is a constant. I just skipped one step of this kind here and directly written the second step over here, right? Let me call this n sub q, call this s sub q, and therefore the signal to noise ratio is and we need to compute this so that we get some kind of a measure of fidelity of this representation. This is a useful measure of fidelity, how good the representation coming out of the quantizer is for the signal. The larger the value of this signal to noise ratio, the better your fidelity, the more accurate your representation, or the less the amount of noise that is being added due to the quantization process. Any questions?
Sir, this x cube, that is the xq square.
Yes.
It's the power in the transmitted signal. It doesn't have to be the signal we are transmitting.
Yes. That is why we must look at this, isn't it? We must look at the signal power.
So is it the transmitted signal power? Is it the actual baseband power? I'm not able to make.
It's only slightly different from it in the sense that it represents the power in the quantized signal.
That which might be far from the original signal.
Not far, it will be close to it, but in any case this is the one which is of interest to us, because it is this power which is going to the receiver, right, and not the unquantized power.
Sir, it is of interest to us only when we know that the original signal to this noise that we are introducing ratio is high.
So why don't we have s minus n divided by n?
In any case, since usually S and S sub q are going to be so close to each other that it doesn't matter very much, because the number of quantization levels typically is going to be reasonably large. So this question is only of academic interest, but nevertheless what I am holding still is that it is this power which the receiver is going to look at, and therefore the signal to noise ratio that is of interest to us is this, should involve this power, the quantized signal power, and not the unquantized signal power, right? And in any case there is not going to be much difference between the quantized and the unquantized signal power, because we are assuming that the approximation is going to be reasonably good, right, of x with xq. So we are assuming that noise power is going to be typically much smaller than the signal power. Alright. Now to proceed further, we have to make some assumption regarding the nature of the signal itself, right? The values of these powers will turn out to be different for different kinds of signals. Must appreciate that, right? In fact, strictly speaking, even the nature of the quantizer that I use should be dependent on what kind of signal I have. The kind of quantizer that we are looking at right now is called a uniform quantizer. Why is it called a uniform quantizer? Because the interval, the quantization intervals is same across the whole interval, right? That's delta is constant across I. It doesn't depend on I. The ith interval, each of the intervals has value step size of delta independent of I. Now this kind of uniform quantizer is actually designed on the assumption that your density function of the signal is actually uniform over the range of its values, right? So therefore let us consider the case, simple case, when we assume that fx(x) corresponds to a uniform distribution function, okay? So we'll take the case of a uniform distribution and complete the computation.
let's assume that your lower value, let's say assume that your interval AB is actually, I'm going to simplify it and say it goes between some minus A to plus A. So your lower limit is minus A and the upper limit is plus A, assuming it to be symmetrical. And therefore your, based on the uniform distribution assumption, your fxx is going to be 1 by 2A when x lies in this interval, x equal to 0 if it lies outside this interval, right? Based on this, let's assume, let's compute n sub q. Now I'm going to replace fxx by 1 by 2A. This becomes all right. What will be xi minus 1? If we have to replace now for xi minus 1, xi and m sub I. As you can see, xi minus 1, in general, let me write down the expression for xi. Obviously it will be the lower most value plus I delta, right? So this will go from minus A plus I minus 1 delta to minus A plus I delta. Also, what about m sub I? M sub I will be x sub I minus 1 plus xi divided by 2, right? Because it's the midpoint of the interval. If you do this computation and substitute here, this is what you get: x plus A minus I delta plus delta by 2 whole square 1 by 2A dx, implying that your m sub I is equal to minus A plus I delta minus delta by 2. This is something that you can easily check by direct computation or direct substitution. Now this is a bit of algebra which I will skip, and I'm sure you can go through the necessary expansion and simplify finally to get if you compute, it turns out that each of those integrals turns out to be equal to delta q by 12, right? And there are q terms in this summation. This is a constant inside the summation. It simply becomes q times delta cube upon 2a into 12. Using the fact that q times delta, what is q times delta? It's the total length of the interval,
2A.
right? Which is in this case 2a. We get the quantization noise n sub q. So q sub delta is 2a. Substituting that here, we get n sub q equal to delta square by 12. Very simple, neat expression for the quantization error. Okay? This is the only step you need to just confirm that the previous integral that I talked about here, this one, through a change of limit, and we change the limits, it turns out to be a very simple integral by substitution for x, and you get a very nice closed form expression like this. Similarly, coming now to s sub q, that is equal to m sub I square and inside was the integral of 1 by 2a from xi minus 1 to xi. right? That is simply delta by 2a, right? That's obvious, because value of the density function is 1 by 2a. We're talking about this. We're talking about this one. This expression here. This is 1 by 2a. The value of this integral will be simply delta by 2a, where delta is the width of this integration interval. Again, substituting for m sub I the way we did just now and simplifying, I am skipping again those simplification steps. That will involve a series summation. Please check up on your own. You get a very simple expression also for S sub q. That's equal to q square minus 1 upon 12 into delta square. And you now get a very nice simple expression for the quantization signal to noise ratio, which is q square minus 1. If you divide this by this, delta square by 12 will cancel out. You're left with q square minus 1. And assuming that q is a sufficiently large number, which it is going to be in typical applications, it's really of the order of q square if q is taken to be much larger than unity. In dBs, it's usually we normally talk about signal to noise ratio in decibels. These are powers, so take 10 log of both the sides, you get 20 log to the base 10 q. Right? So these are the two main results. One is the result for signal to quantization noise ratio, and the other is this, which equivalently sometimes is given in the form of the fact that RMS error that you may expect is delta upon square root of 12. These are the two results which are important results to remember for quantizer characteristics, uniform quantizer characteristics. Yes? Please speak out if you have any questions.
The dB is 20 log A, right?
No, 10 log.
It is 20 log if you are talking of voltage ratios or current ratios. It is 10 log if you are talking about power ratios, right? Any questions? This result can also be made slightly more interesting into a rule of thumb kind of result. If you remember that q is a power of 2, right? So if you take q to be equal to 2 to the power n, then this will become 20 log 2 to the power n, which you can write as 20 n log 2 or 6n. Yes, you're right. 20 log 2 is 6, so that is 6n. Right? So that's a very interesting result, and that gives you a very simple rule of thumb for calculating how much signal to noise ratio you're going to get in dBs depending on the number of levels you use. Right? If you use, for example, a number of levels corresponding to 7 bits, right, you're going to get a 42 dB signal to noise ratio, which is very good. Right? Usually for voice communication you use a signal to noise ratio of between 40 and 50 dBs. So 7 to 8 bits are adequate for representing voice signals in PCM. But the number of levels that we are talking about then is 128 to 256. Right? So very useful relation to keep in mind. So for speech, if you use 8 to 16 levels, which will correspond to 3 to 4 bits, right, the quality is quite poor, but the intelligibility is very good. Right? You get quite intelligible speech, but poor quality. That is, you will hear also a lot of distortion along with the information. 128 to 256 levels is quite good quality, what we call telephone quality speech.
What name is given to first one?
We very rarely use it.
We rarely use it.
Very rarely use 8 to 16 levels, right? It's just to give you some information as to how many levels are necessary, right? If you use these many levels, you lose a lot on quality, because both are important, not only intelligibility but also quality. So usually in most PCM, commercial PCM systems that you use, you have actually an 8-bit representation, right? Any questions? I can stop for a minute just to answer all kinds of questions that you may have so far.
We haven't performed these analysis on the delta modulation.
I'll talk about it. I had planned to do it after doing this for the PCM, right? We'll be doing that for delta modulation also. We are not yet finished with delta modulation. We'll be coming back to it. Any other questions? Because what we like to do is compare on the whole how delta modulation and PCM compare with each other, and compare both of them from the point of view of bandwidth requirement, from the point of view of signal to noise ratio that we can get, and then get a feel for which is better, if at all, right? Now this discussion that we have done was for the case of uniform quantization, as I mentioned just now a few minutes ago. And it makes sense to use uniform quantization provided that you have a reasonable basis to say that your signal is of the kind where its values are uniformly distributed over a certain interval, right? If, for example, you know that most of your signal values are going to lie in a smaller range and the larger values are going to be much less frequent to occur, the probability of having larger values of the signal is small, let's say, just for the sake of assumption, then intuitively you may feel that uniform quantization process may not be a good idea to carry out, right? Because you're going to use or waste a large number of levels in a region where the signal has a very low probability of occurring anyway, right? And you're wasting your number of quantization levels. Given a number of quantization levels, it makes sense to make them more finely distributed in that region where the signal is likely to take values with larger probability than in those regions where the values are going to occur with smaller probability, right? So therefore, this is not a good idea to work with if your signal is known not to have a uniform distribution, right? And then you go for what is called non-uniform quantization. Yes, please.
Also, the derivation only applies to the uniform quantization.
The derivation that we have done applies only to uniform quantization, and also assuming that the distribution function associated with the signal is a uniform one, right? But still, even if it is not so, this is still a good rule of thumb to work with, okay? But let's come back to the concept of non-uniform quantization. So basically what we are going to now do is not use a uniform step size across the whole interval of quantization, but use a variable step size. All right? And it can yield a significantly higher SNR if you do this, higher signal to noise ratio, when your PDF or the probability density function is non-uniform. Which is a usual case in practice,
It's very rarely uniform in practice. Another way of looking at why this may give better results is, one way I have already given you, is by putting less number of levels at, let's say, larger amplitudes, you are going to incur larger errors when the corresponding signal values are also large, right? So that also masks away the error quite a lot. You have large error associated with large sample values and small errors associated with small sample values. That's another way of looking at it, but I still think the better way of looking at it is that the large values occur less frequently in practice, and we can therefore occasionally tolerate large errors, and they'll contribute much less to the mean square value than the small values which occur more frequently. And if they are associated with large errors, then your overall mean square error is going to go up.
Can we have some adaptive quantization?
Yes, we can. That is, if your signal is a very good suggestion, and in fact it is practically used in many applications. That is, you can make your quantizer characteristics dependent on the input signal that is coming along, and it can be made adaptive to the extent that you may not know what the a priori density function is. It can try to adapt to those characteristics, but usually these kinds of things are more complex and outside the scope of our discussion here, but that can be done. Let's take the case of a signal having a Gaussian distribution. I have a couple of minutes more, so I'll just talk about it today a little bit, then we'll take it up in detail next time. Let's say we have a signal with a Gaussian distribution. So as you can see, this is a PDF. This is the value of x. This is the density function. I have plotted the density function. As you can see, that small values of x have much larger probability associated with them than larger values of x, which lie in the tail of the distribution, right? So it doesn't make sense to crowd the quantization levels equally across the whole interval, right? And usually what you'll do is you'll have closely spaced levels in these intervals. Of course, I have drawn a very crude picture here with a very small number of levels. In practice, the number of levels will be much larger, but you can see that these intervals are smaller than these intervals, and this is a good thing to do, right? In practice, we'll like to space them out as you go farther and farther away from the mean value of the signal if you have a Gaussian distribution, right? So the boundaries now, x1, x2, x3, x4, x5 and so on, are not uniformly spaced. Not only that, it may not be the best thing to do to choose the quantization level to be the middle point of the interval, right? It may be proper, it may be all right perhaps to use a slightly different value than the midpoint, because you don't have a uniform distribution even within an interval, right? So when you have a non-uniform distribution, the proper way of designing the quantizer would be to ask the question how to choose the values of x sub i's and the values of m sub i's so as to choose these set of values so as to maximize SNR, right? That is what a proper quantizer should worry about, right? And that is how non-uniform quantizers are actually designed, by looking at the actual distribution and then asking this question as to, for this distribution, how to choose this xi's and mi's for a given number of total quantization number of intervals so as to maximize signal to noise ratio. Okay, we'll take up this discussion next time in detail.